All right, today we're going to take a look at integration by substitution, which gives us a method of finding antiderivatives of more complex functions. It's the equivalent of the chain rule for antiderivatives. So we can use the chain rule to take the derivative of more complex functions. For antiderivatives, if we encounter a more complex function, we will often need to use some other method of finding the antiderivative. One of those methods is substitution. Okay, so let's work through an example here and just kind of see how things work. We have the integral of x plus 2 to the power of 5. We're going to take that x plus 2 and we're going to let that be u. If we took the derivative of u, we'd get du. If we took the derivative of x, we'd get dx. So if we replace x plus 2 with u, we get the integral of u to the 5th. We replace dx with du since they're equal. If we take this antiderivative, we get 1/6 u to the 6th plus c. And now substitute back in, replace u with x plus 2, and we get our antiderivative. Now you likely could have done this one without using u substitution, but this is illustrating the method that we use. Okay, so let's take a look at this one here. We're going to use u substitution. One thing we look for to see if u substitution is going to work is if you can find a function and its derivative. And here I see the function 1 plus x squared. The derivative of that is 2x. So I'm going to let u equal 1 plus x squared. If I take that derivative, then du equals 2x dx. So I replace 1 plus x squared with u. Since du equals 2x dx, I can replace 2x dx with du. Then I can take the antiderivative, and I can substitute 1 plus x squared back in for u. So this method was able to work because we had that 2x there. We had the derivative of the stuff underneath that square root. That allowed us to use u substitution. Okay, let u equal 4x minus 1. Then du equals 4 dx. And notice if we let u equal 4x minus 1, that just leaves us with dx. So rather than writing du equals 4 dx, let's write 1/4 du equals dx. All right, then we let u equal 4x minus 1, so we get root u. dx is equal to 1/4 du, so we replace dx with 1/4 du. Now we take that antiderivative, simplify, and substitute back in. Okay, let u equals 7x plus 5, then du is 7 dx, which means 1/7 du equals dx. So we write the integral of cosine of u times 1/7 du, take the antiderivative, and then substitute back in. All right, we see x cubed, so we let u equal x cubed. The derivative of x cubed is 3x squared, and I see that I have an x squared out there. I need to move the 3 over. So now I can replace x cubed with u, and x squared dx is equal to 1/3 du. So we have integral of sine of u. I brought the 1/3 to the outside, and I have du at the end. And then I can substitute back in. All right, let's see. We're always looking for a function and its derivative. Now, the function is going to be inside of another function. So we have sine of x being raised to the power of 4. So our value of u, or our function for u, is going to be sine of x. The derivative of sine is cosine. So integral of u to the 4th du, since cosine x dx is all equal to du. Take the antiderivative and substitute back in. Now we can take this one step further and we can evaluate definite integrals using this method. So we take the integral from 0 to power 4 of tangent secant squared. Well, I know that the derivative of tangent is secant squared. So u equals tangent, du equals secant squared. And we can find new limits of integration based off this. Since u equals tangent, and x goes from 0 to pi over 4, u of 0 is tangent of 0 or 0. U of pi over 4 is tangent of pi over 4 or 1. So you have the integral from 0 to 1 of u du. Now what's really nice about this is this means we do not need to substitute back in for u. We've found limits of integration in terms of u, so we can evaluate this integral directly from the form that we have it. Take the antiderivative and evaluate from 0 to 1, and we get 1/2. You could have replaced u with tangent after taking the antiderivative, but you would then need to evaluate from 0 to pi over 4. Either way is perfectly fine, so choose the method that you're the most comfortable with. If we use the original limits, we can't go from 0 to pi over 4 because those are values of x. We could leave off the limits of integration, take the antiderivative, then when we substitute back in, we would put those limits back on. And then you could simplify, and then again you'd get 1/2. It's usually a good idea to just go ahead and change the limits to begin with, and then evaluate entirely in terms of u. Okay, we're trying to find a function and its derivative. The function I see is x cubed plus 1. The derivative is 3x squared. If I find new limits of integration, I'm going from x is negative 1 to 1, which means u goes from 0 to 2. Take the antiderivative using my new limits of integration, and I can simplify.